Okay, good morning, everybody. I've been having some interesting conversations with some students about uh, learning in this course and what's required and whatnot. And I'd like to share a couple of ideas with you about that before we actually get started talking about physics. So I want to talk about two things. One is just kind of the expectations in this course, and one is about using the textbook, actually. So let me start by showing you a diagram. So this is a diagram that some of you may have seen before, and it represents a thing called Bloom's Taxonomy of Educational Objectives. And what it tries to get at is the idea that you can learn things at different levels, which you know, right? So and that these levels are, but what it tries to capture is that these levels sort of build on each other and increasingly involve mental effort and creativity. So the bottom level is just called remember, and that's basically rote learning. Okay, we're calling facts and basic concepts. What's the S in the equation for the spring force? Okay. And understand is a little bit higher. It means that you understand what an equation means, for example, or what an idea means, and that you can explain what each of the terms in it means. This is a very basic level. And some people have expectations of a physics course that this is basically the level you'll be operating on, that what you'll do is there'll be a list of problems we know how to solve. There'll be one equation for each problem. What you'll learn in the class is to match the equation to the problem and then plug numbers in it. This is something that you actually come into the class able to do. You can already plug numbers into equations or you wouldn't be here. And this is basically the kind of thing you'd expect of a technician, basically being able to use an equation to solve a problem that is well understood and whatnot. We're actually going for something higher. We're going for the next two levels here. So our goal is more on the apply and analyze level. We want to, in particular, the really key thing is that we want to be able to use information in new situations. We want to be able, in our terms, to apply a physics principle, a fundamental physics principle, to a situation that we haven't ever seen before. When you can attack a really new problem. So in homework, you had to look at, I can't remember, I think it was a fission problem. This is not something that you've memorized how to do, but you have the basic understanding of how to go about solving a problem like that based on fundamental principles. Draw connections between ideas. You're getting to a point where you should be able to start choosing what fundamental principle to use, okay? So that kind of thing is what we're aiming at, and not just a list of equations that you plug numbers into and match to problems that you've already solved. We're aiming for something where you'll actually remember something about physics after you're done with this course. If you've had a course where you just had lists of equations, you might ask yourself, what do you actually remember a year later? The answer is probably not a lot. But here you can actually, the goal is for you to be able to use fundamental principles and start from them, remember them, and apply them to any situation. So given that goal, this sort of has implications for how you study for this course, how you pay attention during lecture, and how you use the resources that you have. And you should be asking yourself questions like, what was the most important idea in today's class? Because not all ideas are equally important. You should be asking yourself, how is what I'm learning related to what I learned before? You should be asking yourself, how is what I'm learning related to fundamental physics principles? So what we're going to do for attendance today is, at the end of class, I'm going to give you 2 minutes, and I'm going to ask you to type into chat what, in your opinion, is the most important idea discussed in today's class. And there's not a single right answer. There are some wrong answers. So if you say it's the function of mitochondria in a cell, I'll know that you were studying for biology and not actually doing physics. But I'm asking for your judgment on what was important in the class. So that's what we're going to do for attendance today as an experiment, and we may do it from now on, actually. Okay, now I'd like to show you also one thing about using the textbook, which has also come up in some conversations with students. Let me go to Canvas here. And let's go to Wiley Plus. When you get to Wiley Plus, you'll see, I mean, there are assigned readings and whatnot. So if you just go to assignments, you'll find assigned readings and whatnot. And that's mostly there for your convenience. So you can read the assigned sections. But you can also find out what sections are assigned by looking at the syllabus and the course calendar. And if you go to this section called Read, Study, and Practice, you'll find a different way of looking at the textbook. So we can choose a chapter here. Let's choose chapter 7 because that's what we're on. And we see that there are the usual pieces. There's the table of contents and whatnot, but there's some pieces that don't show up in the assigned readings often. So there is, at the end of the chapter, a summary page that actually has a summary of ideas and equations that are discussed in the chapter. There are all of the homework problems are also here in this book, and you'll find that all of the odd numbered problems actually have answers. So if you're looking for a way to get more practice, you can work these odd numbered problems and then actually see the answer to make sure that you've actually done it correctly. When you're reading the textbook, so you'll find often that there are these questions in line. It says, question, can you think of a function s's derivative with respect to s's case of ss? What you need to do here is stop and ask yourself that question. Say, I know I'm going to read on and find the answer, but let me see if I can figure it out. These questions that are interspersed through the textbook are an important guide to reading a physics textbook, which is you don't read it like a history book or like a novel. The information is very dense in a physics book, and you have to stop and check to make sure that you've understood something and that you can apply it. So you should definitely try to answer those questions before reading on. And when you get to a checkpoint, you should actually answer it. Okay, so you should actually answer this. So there aren't worked out solutions in the book. There are worked out examples in the book. Okay, so so here's a worked out example right here, and it basically shows you how to approach a problem of this kind. And what you should get from a worked out example is to, no, there aren't worked out examples in the book. And that's one of the reasons that help sessions are good. There is or used to be a student solutions manual for this available from the publisher, but I'm not sure how you get that. But the basic idea really here is that it's not that you need an example for a worked out example for every problem, is that if you actually study worked out examples with the thought of, and you don't memorize what was done, but you reflect on the approach, then you'll actually find that you can apply that approach to other problems. But again, that's the value of these help sessions. You can go and work on problems, get help understanding how to work problems out, that kind of thing. So you need to be taking advantage of those resources. Okay. Today we're going to continue talking about internal energy, which is what we were talking about before. So I'll remind you that last time we looked at we talked about potential energy of springs because of our ball spring model of a solid. And we talked about the fact that inside a solid object, the atoms are always moving around. And so the springs are compressing and stretching. The atoms may have kinetic energy, there's potential energy stored in the springs. And so this is one of the things we mean by internal energy. Now, internal energy is a little bit more extensive than that, and we'll see that there can be other forms of internal energy. For example, if you throw a frisbee, how do you calculate its kinetic energy? Well, its kinetic energy could be half times the mass of the frisbee times its speed squared, a half mv squared. But that doesn't take into account the fact that it's actually rotating, and surely there's some energy involved associated with rotation. And so there's other kinds of energy that we can call internal energy, but right now we're interested and we're focusing on today this energy associated with the microscopic motions of particles inside an object. We're going to call that thermal energy. So we can write internal energy. It's often useful just to lump whatever we don't want to think about at the moment into internal energy. So something could be vibrating. If we had two tennis balls connected by a rubber band and we threw that whole thing, it could be vibrating. So that's vibration. Something could be rotating. We could have this randomized thermal energy. There can be energy stored as chemical energy, the way they are in living organisms. There could be other things. And so what we're focusing on right now is this part that's actually associated with temperature. So there's nothing mysterious about thermal energy. It's just this microscopic energy associated with the vibration of atoms. And so if we have, let's go back to our ball and spring model here. So what we're talking about is thermal energy here is just the energy that these atoms and these bonds have in ordinary matter at any temperature. And there's nothing mysterious about it. I mean, if we could just take this atom if we knew the speed of each atom at every time and the position of each atom, so we could get the compression or stretch of the springs. We could just add up the kinetic energy of every atom and the potential energy of every spring, and that would give us the thermal energy in this object. Now, we can't actually know that, and so we need some sort of macroscopic quantities to do this. While we're looking at this, though, it's interesting to think about how we would measure macroscopically the temperature of say a solid object, a block of, let's make this a block of aluminum. So how would we measure its temperature? Well, how do you measure the temperature of something in real life? Use a thermometer, right? So to measure the temperature of this block of aluminum, we might put a thermometer in contact with this object. How would that work? So energy gets transferred into the thermometer, yes, but how? It looks like, so if you imagine a thermometer is, let's imagine an ordinary thermometer that's got a glass container and some liquid in the container, okay, and the liquid moves up and down, old-fashioned thermometer. Well, what's going to happen is the atoms in this, the moving atoms in this object bump into the atoms of the thermometer. They collide with them and they make them move. So some of the energy from our object that we're measuring is transferred into the thermometer due to these collisions, and now the atoms in the thermometer are actually moving more. And therefore, since the atoms in the thermometer are moving more, they've got some of the thermal energy that the object we're trying to measure had. Now, in the kind of thermometer we're talking about here, a liquid thermometer. And there are plenty of other kinds, but the basic idea. So this is the sum of all the K sub i's plus the U sub i's. But a thermometer, we're talking about a liquid thermometer. So what happens is the liquid expands, right? And it moves up the tube, and you read it off a scale. So we're talking about, you know, this kind of liquid thermometer. Why does volume increase with temperature? So volume increases with temperature because you can actually see this from the potential energy curve that we drew for neutral atoms bonded together, this Morse potential energy, which actually looks kind of like this. And we can see here that this potential energy curve is close to a parabola, but it isn't really a symmetric parabola here. It actually gets wider as it goes up. And therefore, for a given value of k plus u, the equilibrium position is actually going to be a little bit different. As the potential energy curve gets wider here, the equilibrium position so this is energy and this is separation. The equilibrium separation gets a little bit larger. So these atoms are moving more and the whole thing expands. It's true of a solid too. So one of the ways a thermometer can work is just from expansion. As more energy gets into this system, the equilibrium separation gets larger and larger. Temperature 1 and temperature 2. And temperature is, so temperature is roughly here a measure of energy inside the solid. So here's a question. We have two lead bricks, one moving in the x direction and one moving in the minus x direction. They each have the same kinetic energy K. They come together, smash into each other, and come to a stop. So what happened to their energy? So the alternatives are the kinetic energy changed into rest energy, the kinetic energy changed into thermal energy, the total kinetic energy, the system decreased by an amount 2K, and since the blocks were moving in opposite directions to start, the initial kinetic energy of the system was 0, so there was no energy change at all. Yeah, so temperature is basically a measure of the energy in a substance. So when the air is hot outside, the air molecules have more kinetic energy. They're moving around faster than if it's cold. So most of you said that the kinetic energy changed into thermal energy, and that's correct. The atoms in the blocks are now moving a lot more than they were before the blocks collided. If you said 4, this is why we need to know the definition of kinetic energy. This is why you can't just look it up every time. So can kinetic energy ever be negative? How can half times the mass times the speed squared? Okay, so it doesn't matter what direction you're moving in, your kinetic energy is always going to be positive. And that's why there's some things you just need to know. So indeed, the energy changed into thermal energy. This basic idea is actually called energy. We call it energy dissipation. Where energy is something like kinetic energy is converted into randomized thermal energy. And so energy into randomized energy. And there are other examples of this that we already know about. So, for example, friction. So we have sliding friction. What happens when you slide, you repeatedly take, say, a box, a cardboard box, and you rub it back and forth across a table? Well, if you do it enough, you can feel that both the box, the temperature of both the box and the table increase, right? They feel warmer. And some of the kinetic energy, some of the energy you're expending here, some of this work you're doing is actually going into this randomized energy that's making the atoms in the box and the atoms in the table move more. So that's an example of dissipation. And this force we know already, so the magnitude of the friction force is equal to some constant that we call the coefficient of kinetic friction times the normal component of the force exerted on the object by the surface. There's a thing called viscous friction, where the magnitude of the friction force is actually proportional to the speed by some constant that's often called V. And there's air resistance, where the magnitude of this dissipative force is actually proportional to the speed squared with some constant that's can call C. And in each case, what you're doing is transferring energy to the environment, and the environment's actually getting hotter. So the energy is, not, however, not disappearing. It's actually, so dissipation isn't maybe a great term, but it's still there. Like when you rub your hands when it's cold, exactly. Yep, that's right. So at the macroscopic level, we can do some calculations about what's happening. So we can say that the amount, there's a quantity that we can define called heat capacity. And it's the amount of energy required to raise the temperature of an object by 1 Kelvin. And this is an extensive property. In an intensive, so an intensive way, it would be per mass, per gram, or per kilogram, or per mole. You're going to find it. Okay, and that's so. So one example is it takes 4.2 joules to raise the temperature of 1 gram of water by 1 Kelvin. And note that 1 Kelvin equals 1 degree Celsius. So the scales have different zeros, but the size of a degree is the same. So raising something temperature 1 degree Kelvin is the same as raising its temperature 1 degree Celsius. So heat capacity, and this is a capital C, is 4.2, in this case it would be 4.2 joules per gram per degree Kelvin. So it's the energy input required per gram per to raise something 1 degree Kelvin. And so this tells us already that the different substances are really different, and this is because of their internal structure. So the amount of energy you have to put in to raise a gram of water 1 degree Kelvin is quite different from the amount of energy you'd have to put in to raise a gram of aluminum by 1 degree Kelvin. So this depends on the internal structure of the objects, composition of the objects. And so we can actually calculate, though, the increase in thermal energy of an object by using the heat capacity, but we're going to need some other information. We're going to need the mass, and we're going to need how many degrees Kelvin we change the temperature. So the change in thermal energy is going to be the mass times the heat capacity times the temperature change. So one way to raise the energy of something is to do work. So energy input raises temperature, and one way to do it is just through mechanical work, which we already know. So let's say we have a container of water, and it's 500 grams. And what you're going to do is you are going to take it and you're going to shake it sideways. And you're going to move it, say, 1 meter in each direction, and you're going to do it 500 times. And let's say you're exerting a force that's roughly equal to its weight. So the force you're exerting is about half of a, so 500, so it's going to be, 500 grams is going to weigh about half a kilogram. So let's say your force is approximately equal to mg, so it's 0.5 kilograms times roughly 10 newtons per kilogram, we're estimating here. Okay. So how much would we raise the energy? So we have, we can solve for delta T here. So the question is, if we did this, how much would the temperature go up? So we would, so over m times c. Well, let's see how much work you did. Your work here, work is, so you move it back and forth. So that's twice. You're exerting a force of about 5 newtons. You're moving it through 1 meter, and you do it 500 times. So you have 5 Newton force times 2 is 10 times 5,000. So we have, you've done 5,000 joules of work. So that's our energy input. And that went into thermal energy. So we have 5,000 joules divided by the mass, which is, now so Marco says, do you use grams or kilograms? And the answer is you use whatever you're given. So we knew here that heat capacity of water is, what do we say it was, 4.2 joules per gram per Kelvin. So we're going to use grams here. So 500 grams times 4.2 joules per gram per Kelvin. And that's going to come out to 2.4. We raised the temperature of this thing 2.4 Kelvin. And you'll find it given in different units. So that's how we'd calculate energy change due to mechanical work. But how would we calculate energy change due to, there's other things, like we talked about just putting a thermometer in contact with something. Energy flows from one object to another. So there's another kind of energy transfer. So we have a new kind of energy transfer. We have energy transfer due to a temperature difference. And there's a physics symbol for this. So so we can actually add this to our energy principle. So here's our energy principle. So we can write the change of energy of a system, E final minus E initial. We had work, but now we get to add energy transfer due to a temperature difference. And that's given the symbol Q. Now Q is energy flow from surroundings to the system. So it can be positive or negative, because energy, if you put two things together and if the surroundings are hotter than the system, energy is going to flow into your system and Q is going to be positive. But if the surroundings are colder than your system, energy is going to flow from the system to the surroundings and Q is negative. So that just gives you the direction of energy flow. Now there's a technical word in physics. This thing Q is often actually called heat. And that's really a confusing term, because we always think of heat as related to temperature, and it's not in this physics definition. It is this amount of energy that flows from the surroundings to the system. And so we're actually not going to use this word. We're going to call it energy transfer due to a temperature difference, which is a lot of words, but it's actually super clear. So that's the word we're going to use. Okay. So let's see if we can apply this idea about the new way of writing the energy principle here. So here's our situation. We've got a pot and it has 1,000 grams of water, and you put it over a fire, which is hot, and you're also stirring the water with a paddle. And we're going to take the water as the system. So the fire is at a higher temperature than the water. There's energy transfer due to a temperature difference. You can also call it microscopic work of 500 joules to the water. And at the same time, you're doing work by stirring it. So there's external work done on the system. And so the question is, what's the increase in the thermal energy of the water? So most of you, by far the majority, said 5, and that is correct. And all we're doing is just applying our equation for the energy principle here, right? So we have the change in energy of the system is W plus Q. So we did 2,000 joules of work, and there was 5,000 joules transferred due to a temperature difference. And so 7,000 joules of energy were put into the system by these different mechanisms. And that's the increase in the energy of the system. So which of the following statements is correct? So are Q and delta E thermal the same thing? They're not the same thing, but they're equal. Oh, so Emily asked a good question. So she says, wouldn't the stirring give the water rotational energy? And initially, you're absolutely right, it would, right? The water would be swirling. But then what happens when you stop stirring? The swirling dies down. Where did that energy go? Well, it goes into the random thermal energy inside the system. So this thermal energy that we're talking about is due to these random motions of the atoms inside an object. Okay, so it's sort of microscopic kinetic and potential energy, right? Whereas if this beaker of water was you threw it through the air, then it would have some speed, and then it would have, the whole object would have kinetic energy. Okay, let's see if a few more people can answer this question, because this is an important question. Okay, so if we actually bother to do a question, it usually is important, and this one is particularly important. Okay, so the majority said 3, which is correct. And we saw that up here before, because the change in, so the change in, if the part of the system energy that changes is the thermal energy, it can be changed by work or by, it can be changed by mechanical work, or it can be changed by energy transfer due to a temperature difference. So this number can be bigger than Q because there was additional work, like in that previous question. It could be smaller than Q if the work done was negative, that is, the system was somehow doing work on the surroundings. And so they're not the same thing, and they're not always equal, and they're not always positive, because energy can flow either way. Something can lose thermal energy or gain thermal energy. Energy can be transferred into the system or out of the system due to a temperature difference. So this is important. So let's do a problem where we use heat capacity and we're only focused on energy transfer due to a temperature difference. So here's an example. We have a block of aluminum. It's 300 grams. And its initial temperature is 500 Kelvin. And we have a block of iron, which is 650 grams, and it's at 300 Kelvin, so a lower temperature. And we put the aluminum block on top of the iron block in an insulated enclosure. So that that no energy can flow into this system. We've isolated it from its surroundings. So this is isolated. And so what's the question going to be? What is the final temperature? Now we need some data. So data, we have the heat capacity of aluminum is 1 joule per gram per Kelvin. And the heat capacity of iron is about 0.42 joule per gram per Kelvin. And if we wait long enough, we actually know these things are going to come to the same temperature, right? They're going to come to what we call thermal equilibrium. Because these blocks are in contact and energy can flow back and forth between the blocks. But so the question is, what is that final temperature? So we start again with the energy principle. So the change in energy of the system is equal to the change in energy of aluminum plus the change in energy of the iron. And that's going to be equal to the work done by the surroundings and energy transferred in from the surroundings. So if we pick the system as both blocks, then we know that no work is done by the surroundings and no energy can flow in from the surroundings because we're in a very well insulated container here. So that's going to be equal to 0. So we have 0 is equal to the change in energy of the aluminum plus the change in energy of the iron. And that's going to be equal to the mass of the aluminum times the heat capacity of aluminum times the change in temperature of the aluminum. So this is T final minus T initial, plus the mass of the iron times the heat capacity of the iron times the change in temperature of the iron, which could be different because the iron's colder and it's probably going to get warmer, the aluminum's going to get colder. So it looks like we've got a problem here because these two delta T's are different. C is the heat capacity of the particular metal, right? And it's a capital C, not a small c. So we can actually write this out as the mass of aluminum times the heat capacity of aluminum times the final temperature minus 500 Kelvin, which was its initial temperature. So that's delta T for the aluminum. And we can write this term out as the mass of the iron times the heat capacity of the iron times, well, let's expand this delta T here for the iron. So it's the final temperature of the iron minus 300 and 300K. And now we can plug in all this stuff, but notice that we now have an equation that has one unknown. So because the final temperature has to be equal at equilibrium. And so we can solve this for T final, right? So we could plug in numbers here. In fact, why don't we do this in VPython? So let's see what we're going to get. We're going to get mass of aluminum, heat capacity of aluminum, T final minus mass of aluminum, heat capacity of aluminum times 500 K plus mass of iron, heat capacity of iron times T final minus mass of iron, heat capacity of iron times 300K. So we have T final times mass of aluminum, heat capacity of aluminum plus mass of iron, heat capacity of iron minus so T final is going to be, it's going to be the mass of the aluminum, heat capacity of the aluminum times 500K plus mass of iron, heat capacity of iron times 300K divided by mass of aluminum, heat capacity of aluminum plus mass of iron, heat capacity of iron, and that looks really annoying. So let's do that in VPython. And this is why VPython is such a great calculation tool. And I'm doing this in part because people have asked for me to do more of this. So I'm happy to do it. So let's get some numbers in. The mass of the aluminum is 300 grams, and the mass of the iron is 500 grams, no, 650 grams. And the T initial of aluminum is 500K, and the T initial of iron is 300K. And heat capacity of aluminum is 1, and heat capacity of iron is 0.42. And so T final is mass of aluminum times heat capacity of aluminum times initial temperature of aluminum plus mass of iron times heat capacity of iron times the initial temperature of the iron divided by and if I didn't make algebra mistakes, which is always possible. And no employed multiplication. Right. And a typo. So we have a number. So you guys are good debuggers. Good job. So notice that we did have to do some algebra on paper to do this calculation, but once we did it, it was actually a lot easier to do this way. And if I discovered that I had the wrong number for the mass of the aluminum or an initial temperature, I could change that. What if the problem really said that the initial temperature of the iron was actually 350? then I'd get an answer for that too. I don't think there's any way around algebra. You just have to do it. So what do we get? I'll write it down. 404, right? So notice that that one block, the thermal energy of one block decreased in this situation. Okay, so the aluminum is now at 404 Kelvin instead of 500 Kelvin, so it got cooler. So energy flowed out of it. So for that particular, if you took that block as the system, Q would be negative. Okay. So we've talked here about equilibrium. And that's the state we got to where there was no energy flow. For a while, energy flowed between, from the, which one was warmer? From the aluminum block to the iron block. And then after a while, they got to the same temperature and energy flow stopped, and that's equilibrium. There's also a different kind of situation that we call a steady state. And the energy of a system can be constant, but despite the fact that there's energy flow from the system to the surroundings. So in the winter, when you heat your house, you don't get it warm and then turn off the furnace and it stays warm. You have to leave the furnace on. Why? Well, energy is flowing from the house to the surrounding air. It's heating the surrounding air, and so in the ground, and so you need to keep putting energy in, but the temperature of your house isn't changing. So, and there's also, so in this situation, you never do get to equilibrium, but you can still have constant energy content. Okay, so we can also define the rate of energy flow. So rate of energy flow, and that's power. So that's just energy divided by energy per unit time. So 1 joule per second has a name. It's called 1 watt. And often energy consumption of things is rated in watts, right? So you have light bulbs that are 100-watt light bulbs, although not very much anymore. They've gotten more efficient now that we use LEDs. But let's consider one of the old inefficient 100-watt light bulbs. So let's say how much energy is required to run a 100-watt light bulb for an hour. Well, this 100 watts tells us the rate of energy use of the light bulb. So energy is going to be equal to 100 joules per second times the number of seconds. So we have 60 seconds per minute and 60 minutes per hour. And so we get 3.6 times 10 to the 5th joules are required. In a homework problem that you weren't really ready to do, it actually asked about the energy per cycle of a spring mass oscillator. So there was a homework problem. So you had a mass on a spring oscillating back and forth. Yeah. And so the question is, how do you get the period? So so energy dissipated per period. Well, remember that we had, when we solved we actually were able to write an equation for the momentum principle that we could actually get a solution as a function. And so we had x of t is something called the amplitude, the maximum stretch, times cosine of omega t for this oscillator. And remember that omega turned out to be the square root of the spring stiffness over the mass. So omega is in radians per second. So it's equal to, so it would go 2 pi radians in one complete oscillation. Okay, so if this is x versus t, so this is one period. That distance is the period t. And during that time, we've oscillated through 2 pi radians. So you can actually get the period from the oscillation, and then you can calculate power. Just to make sure that we're distinguishing here between equilibrium and steady state, we have one more question. Okay, so we have thermal energy transfer due to a temperature difference through the walls of a house is usually proportional to the difference in temperature between the inside of the house and the outside of the house. And in one situation, let's say you're keeping your house at 20 Celsius, which is a little chilly, but it's ostensibly room temperature, but it's 10 Celsius outside. You keep it at a constant temperature of 20 Celsius by using energy at the rate of 4,000 watts. And how much power, what would your power usage be? What would your rate of energy use be required to maintain it to be at 22 Celsius, which is warmer? So think about this for a minute. So basically the idea is that if it takes 4,000 watts for a 10-degree difference, that means that it's basically 400 watts per degree. And so if we have 400 watts per degree Kelvin or per degree Celsius times 12 degrees, we would actually need 4,800 watts. So now here's what we're doing for attendance. We'll see if you're really here. I want you to type in chat, and if you're really shy, you can make a private chat, but I'd prefer public chat. What, in your opinion, was the most important concept that we talked about today? okay? And that's what I'm gonna, and there's no right answer. Okay, there's some wrong answers, okay? So it's not, we didn't talk about mitochondria, but there's no right answer. This is your opinion of what the most important idea was that we, no, it's not a cop-out. This is your opinion, okay? So, okay, there's a lot of great answers here. Okay, and I want you to think about your answer, because if your answer is vague and it just says, then you need to reflect a little more on what we're doing. So if your answer is not really related to what we did, and you can't pick one thing that we actually did and talk about physics concepts, then I think you're not getting out of the lecture what you need to. Okay, so I asked for one thing. So if you give lots of things, then it's a summary, which is okay. But I'm asking you to make a decision to decide what's important. Okay, we are done. Thank you very much. A lot of good stuff in your answers. Please be sure to answer before you leave so you can get credit for being here.